Oh, you still need paper, right? There's this random notebook up here.
Now, they help. Everyone really have less. Less people? No, like they got, no, I have like, they give me less amount of help. Yeah, that's unfortunate. I just have to a little bit. What? I just have to a little bit. Oh, yeah. Yeah.
So, Yesterday, at the end of class, I made some informal remarks about this notion of what an improper integral is, right? This is where our domain of integration is possibly unbounded, or another option, we could be considering a function which grows unboundedly inside some bounded domain of integration. That is to say, if it has an asymptote or some such like this, right? So let's start to make these different scenarios a little bit more precise. So an integral from a to b of f of x dx, in which either a or b or both are infinite, or such that f is unbounded in the interval a comma b then we call it improper. So this is basically what I just said in words. Now we want to come up with some computational mechanisms that allow us to give a sensible meaning to this notion of an improper integral, a way to assign a number, if possible, to such a object. Okay, so let's look at an example for how we might be able to do this. Let's consider the function f of x equal to 1 over the square root of x, or in exponent notation, x to the negative 1/2, defined on the half open interval 0 to 1. Okay, just draw a sketch of the graph of this. I really didn't need to come out that far, did I? So this kind of looks like this. Yeah, it's a graph of f of x. Here's the point 1. We're closed here, and we're open at 0. So when we take the interpretation of the integral of a function as the area under a curve, right, we are considering this area, but our function f grows unboundedly as we approach 0 from the right. Right? We never actually get to 0. So what we're dealing with here is something that potentially has infinite area. And I say potentially because we have to ask ourselves the question, how quickly does this function's graph get very close to 0, the vertical line, x equals 0? If it gets there fast enough, there is the possibility that this area could turn out to be finite if we come up with the correct notion of how to compute area. Okay. So, let's just make a couple notes about this. First of all, f is unbounded in this half open interval. So one thing we know for sure, we can't perform usual integration. I.e., we can't take a limit of Riemann sums. Right? Remember when you discussed the definition of the integral in calculus 1, right? We talked about this notion of an integral being defined by coming up with a finite sum of rectangles under a curve, and then gradually increasing the number of rectangles, and decreasing their width, right, to make a finer partition of more thin rectangles, and letting that process go to infinity is how we usually take an integral, a definite integral. Okay? That won't apply here because we can't ever capture this in a finite number of rectangles, right? You have to be able to make a finite number of rectangles in the first place to approximate this. But if we were to try to put rectangles under this curve in this half open interval, we would end up with rectangles that are infinitely tall, no matter what. Okay. So this is what we can do. Instead, what we'll do, we can take a limit of integrals. Right? That is to say, f is integrable in the usual sense, in the sense of Riemann sums, on the closed interval a to 1 for any a greater than 0, right? If we're not going all the way to 0, I pick some point a here. There's no problem with approximating this by rectangles, right? It's a finite area. Okay. So here's what I'll do. Let me come up with a formula for the definite integral going from a to 1 of my function x to the negative 1/2 dx. All right. We briefly stated what the fundamental theorem of calculus says yesterday. How do I find the value of this definite integral? Yeah.
F of 1 minus f of a.
Yeah, what's f in this case?
It'd be the
Yeah, any antiderivative, right? Because remember, there's a whole family of antiderivatives depending on the constant c that we choose to add. But any derivative will get you the same value because what happens here? We have f of 1 minus f of a. No matter the constant that we choose, it'll be the same when we evaluate it at 1 or a, is a constant term. So we have a constant here and then minus the constant here. Right? So in practice, what we usually do is use the antiderivative where c is equal to 0, right? Because it's going to cancel anyway. The constant will cancel anyway. Okay, so therefore, what we have to do to evaluate this is come up with an antiderivative of the function x to the negative 1/2. What is the antiderivative of x to the negative 1/2? Yeah.
It's x to the 1/2 over 1/2.
Yeah, good. Okay, so this is maybe I should write this. Where f of x equals x to the 1/2 divided by 1/2, or 2x to the 1/2, right? And antiderivative of x to the negative 1/2. And antiderivative, right? I chose c to be 0 here because I'm going to evaluate it at these numbers 1 and a. Okay, so what do we get here? 2 times 1 to the 1/2 minus 2 times a to the 1/2, or just 2 minus a to the 1/2. Okay. So now we have an expression for an arbitrary a, which is greater than 0 and less than 1, right? For the integral of this function, x to the negative 1/2. What's our next step? How do we try to make sense of this? Yeah.
Solve for a that approaches the limit.
Yeah. So we want to see what happens as the value of a gets closer and closer and closer to 0, right? So now we take a limit of this expression. So we want to take the limit as a approaches 0 of 2 minus 2 times a to the 1/2. I'm missing one critical detail here. Remember that when we take limits, when we take a limit, when I write something of this form, what I mean is that we're approaching the value, 0 in this case, from both the left and the right. And we can approach from a single side. That just means slightly less. But in this scenario, we're only approaching 0 from one side, right? We're insisting that we approach 0 from the right. Yeah. Okay, so we indicate that by just putting a little plus sign in the superscript of the value. Okay. So what do we know about taking limits? This is just a polynomial in the unknown a. So how do we evaluate this limit? Remember this, taking a limit of a polynomial? Yeah.
I believe you really find the average relationship of a and a plus 8 or something.
So this would be if we were trying to evaluate some kind of derivative, but here we're just trying to evaluate a limit straight up. I think you had your hand up in the back there. Yeah, we can just plug the value in because this is a polynomial, right? It's defined at this point, so we can just plug it in. Okay, so when we plug in 0, what do we get? 2. Okay, so this is now what we take as the definition of the value of the integral that we're interested in. So we take this as the definition of the integral in question. That is to say, even though a priori this does not make total sense to evaluate, this process of taking a limit of integrals gives us this finite value of 2, right? So when I say we take this as the definition, it's somewhat nonsensical to say, okay, I have a shape here, right? It has a straight edge here, a straight edge here, and it has 2 infinite parts that bound it, right? This curve goes on forever, and this curve goes on forever, and they never touch. Yet the area of this thing is finite when we make this definition. Okay, so as we will progress, this is kind of counterintuitive, but it reconciles well with the regular notion of integrability. That is to say, many of the properties that the standard Riemann integral has are also enjoyed by this definition, where we take a limit of integrals to produce a value of an integral that has some infinite bounds. Okay.
Could you apply this to any integral? Or is this only like special cases where you have half a boundary?
So there are many more cases than just this. I'm apprehensive to say, is it any integral? Like, I'm sure there's something that you can construct where this procedure doesn't apply. We will see cases where the limit of the integrals does not converge. So that in fact, the area is infinite. But yeah, that's a good question. Can you construct a function and a region where this process makes no sense? That is to say, neither does it converge nor diverge in a meaningful way. I don't know the answer to that, but I'm not going to say yes or no. Okay, good. Right. So oh, sorry, I skipped some notation here, right? So let's just say really what we did is we took the limit as a approaches 0 from the right of this integral from a to 1 of x to the -1/2 dx. And what we concluded is, in this case, it equals 2. Okay, so I did this piece of notation piecemeal here, right? I did this first and then took the limit of the result. But in general, this is the thing to remember. Okay, so let's give the general definition for this. Let's suppose f is defined on the half open interval close bracket a comma b parenthesis um, where B might be infinity. And for all C with C between A and B. Okay, that is to say, what happens when C is A? Our interval is a point, right? Then you just, when you integrate, you get 0. But of course, I'm not going to allow myself to be B because number one, it might be infinite. So, or we might have an asymptote there. So we just go as close as we want to be. Yeah. For all C with A less than or equal to C less than B, F is Riemann integrable. On a C. Then what can we say? The integral from A to B of f of x dx, which we will also sometimes see written as the integral on the half open interval A to B of f of x dx. This is just the same concept with different notation. Is equal to, here's the part of the definition, the limit as C approaches A, approaches B from the left of the integral from A to C of f of x dx. Okay. So just remind me, what do I mean by Riemann integrable? This is just the standard notion of integration that we learned first, that the integral can be computed as the limit of Riemann sums. If you like, the real difference in this definition from Riemann integrability to this notion of improper integrability is that we're not taking a limit of Riemann sums, we're taking a limit of limits of Riemann sums. Right? There's an extra layer of limits happening. Okay. Okay. So let's continue this definition. If this limit exists, we say f is integrable. On this half open interval, or sometimes we say the integral from A to B of f of x dx converges otherwise this integral diverges. Okay, so during this unit where we're talking about improper integrals, I'll be kind of careful, or try my best to be careful, making the distinction between Riemann integrable, which is the standard notion of integrability, and integrable, which is this slightly generalized notion. But after this unit, we'll kind of blur the line between those two things because formally they behave very much the same. Yeah.
A little before, but that too, is that an approximation? Or is that like, assuming it would go to infinity, it would be like that?
Well, it's not an approximation. It is the value of what symbolically the antiderivative is if we let the values of the limits, and when I say that, I mean the limits of integration, approach where the Riemann integral is undefined. Okay, so this is an exact value of this limit. Okay, and this is the whole business of making this the definition of what this integral is. So I don't think there's any useful way to think of it as an approximation. But I understand your apprehension, right? Again, we have this thing with an infinite boundary that we're saying has a finite area, essentially. The little makes one uneasy, I understand. But we're just saying by fiat, this is what it means to have a finite area, that this limit has a finite value. Okay, good. Right. So we can say something entirely similar. For f on a half open interval of this form, where a might be negative infinity. That is to say, the integral from a to b of f of x dx. Again, this somewhat most likely unfamiliar notation of just putting the entire interval at the subscript of x dx is equal to the limit as c approaches a from the right of the integral from c to b of f of x dx. Right? This is symmetric to what we said, and in fact, this is the form that the example that we looked at first. So, right, we had the asymptote at 0 on the left boundary of the integral. Okay, good. So let's see what this definition allows us to do. Why don't we try to integrate the integral from 0 to infinity of e to the negative x dx. Okay, so what should we do? Well, firstly, let's note that for every positive real number, I put my notes here, b, every positive real number b, e to the negative x is integrable from 0 up to b, right? It's Riemann integrable. So it satisfies the hypotheses of our definition, right? We can attempt to take this limit Okay? So by this definition we just made, this is clearly not Riemann integrable, right? Same problem, we'll have infinitely many rectangles because we go out forever and never cross zero, right? So we're going to take the limit as b approaches infinity. Note that I don't say from the left to the right here, because there's only one way to approach infinity. To come from the left forever, you can't get on the other side of infinity on the real number line. Okay, the integral from 0 to b e to the negative x dx. Okay, so what's the antiderivative of e to the negative x? Yeah.
Negative e to the negative x?
Yeah, right. This is just a u substitution, right?
Yeah.
I mean, that's a little bit overwrought, but yeah, good. So the antiderivative here is negative e to the negative x. So we take the limit as b approaches infinity of negative e to the negative x evaluated at b and 0, or in other words, the limit as b approaches infinity of negative e to the negative b minus negative e to the negative 0. Okay, so I'll rewrite this one more time. The limit as b approaches infinity of negative 1 over e to the b plus 1. So how do we evaluate this limit? Yeah,
It should be 1.
yeah, it's just 1, right? Because this requires us to remember our study of limits from calculus 1, right? As b gets larger and larger and larger, e to the b grows much faster than b, right? So we get something in the denominator getting exponentially large. That means we're getting closer and closer to 0, quite fast, as a matter of fact, right? So this summand goes to 0 as b goes to infinity. And a constant, the limit of a constant is just a constant, right? So we get 1. Okay, graphically, let's just look at this for a second. So this is 1, right? And you get really close to 0 pretty fast, right? So this never actually touches the x-axis, right? We never get 0 or a negative value from the graph of this, right? But this area is what we think of the area under the curve tends to 1. That's because even though it's infinite, we get so close to the x-axis so fast that at some point it becomes negligible, right? Okay. Just want to make sure that I initiate the quiz at the right time. All right. So, no. We define the integral from A to B of f of x dx to be equal to the integral from B to A of f of x dx. Provided that the latter integral exists. Okay, that is to say, since this is a notion that we're now defining, we would do well to have it mimic what Riemann integrals have that is nice about them as best as possible. So we, by fiat, say that if this converges, and it so happens that this converges, they must be equal. Okay. All right. So I think we have time for one more example, and then we'll take the quiz. All right. So what if I ask you to compute the integral from -1 to 8 of 1 over x to the 2/3 dx? Okay, so how do I proceed? Yeah.
So we're from -1 to 0.
Yeah, great. Why is that? Yeah, right. So the integrand, this function, 1 over x to the 2/3, has an asymptote at x equals 0, right? It can't assume that value. So even though the definition we made had to do with the endpoints of the domain of integration, we have to be aware if our integrand is not defined somewhere within the domain of integration. And then we can do exactly what you said and split it up so that we have the situation of our definition where we have two intervals where each of them have an endpoint where the function becomes unbounded. Okay, so we have to notice that 1 over x to the 2/3 has an asymptote at x equals 0. So in order to apply our definition, we will split this integral up by the linearity of the limits of integration. The following. Okay, and now we just use both parts of our definition, right? One where we approach 0 from the left, and one where we approach 0 from the right. Yeah. Okay, so let's just write this down. Very quickly. What do we get? We get the limit as d approaches 0 from the left. The integral from -1 to b x to the 2/3. Sorry, 1 over x to the 2/3. x plus limit as a approaches 0 from the right, a 8, 1 over x to the 2/3 dx. Okay, what is the antiderivative of, what is a particular antiderivative of x to the 2/3? I'm sorry, 1 over x to the 2/3.
Natural log.
Careful, this is a power rule. You only take the natural log when the power is -1.
I was just gonna say, power rule, so you could change the, 1 over x to the 2/3 to x to the -2/3,
Mhm.
and then do the power rule, so you get x to the 1/3 over 1/3.
Yeah, good. Limit as b approaches 0 from the left of 3 times x to the 1/3, right? Divided by 1/3, just split the fraction, you get a 3, right? Evaluated at -1 and b plus the limit as a approaches 0 from the right of 3 times x to the 1/3, evaluated at 8 and a, about 8. Okay, so altogether, what do we get? We get the limit as b approaches 0 from the left of 3 times b to the 1/3 minus 3 times -1 to the 1/3. Okay, plus the limit as a approaches 0 from the right of 3 8 to the 1/3 minus 3 times a to the 1/3. Okay, what do we notice right away? I can just plug in 0 here, right? Because this function is defined at 0. So we get this goes to 0, and this term also goes to 0. Okay, what's the cube root of -1? It's also -1. Good. So we get this is equal to -3 times -1. We get 3. Okay, what's the cube root of 8? 2. Yep. Times 3 is 6. 9. Okay. Again, this is surprising because what does the graph of this thing look like? Okay, here's -1, here's 8, and we approach 0 like this again in a way that's fast enough that we become negligible after a certain point. So this is great, right? We were able to make a definition that allows us to compute finite areas for things that have potentially infinite boundaries. Kind of cool. We'll see a lot more about this next week. But for now, let's get ready to take the quiz. You won't need a calculator. And if you feel like that's wrong, just leave your answer in whatever format you can put it in. But I don't really think you will. So yeah, there's a front and a back. 3 questions. Please just don't start until everybody has a quiz. The worst part about being in person, passing out tests. I guess the threat of COVID is pretty bad, too. Okay, everybody has one, right? Yeah. Okay, go ahead. I'll have till the end of the class period. 10 minutes left. 2 minutes. Okay, please stop working. Make sure your name is on your paper and please bring it to me at the front. I want to try my best to try to learn your names. I have 160 something students this term, so it might be tough, but I want to try. So please bring your paper up and I'll try to associate the name with the person. Thank you. Thank you very much. Thank you very much. Thanks.
And I have been out of the door.
Yeah, okay, great. Thank you. Great, thanks. Right, thank you. Thank you very much.
I'll be doing it for hours. Hours. And nothing in our. It's just so big. Why can't we just explain to us, like,
That's okay.
The other thing is, like, I did all of them. It was no problem.
Right, right. So remember, I said at the beginning that the students would be particularly difficult. Don't worry, you're not going to be penalized for how hard they are, right? It's to help you get a sense of how hard it is.
That was the main.
This will make it much easier for you to do everything. That's kind of how this starts. I'm gonna set out the solution. Yep.
I think at one point.
Okay.
Oh.
I'm sorry, say that one more? So if you look on the campus homepage, on Tuesdays they're on Zoom, on Wednesdays they're in person.
And one more thing, like, that they're supposed to take notes from, and as far as I understand, you write the title of the chapter and then numbers of the exercise, right?
Yeah, so let's just take a look.